Zynq SoC. In this project, we are using a PS and PL co-design approach on ZedBoard, where the processor system, ARM processor, and programmable logic FPGA works together to achieve faster image processing. Coming to this project, we are using Vivado 2023.1 version. In this 2023.1 version, we need to first create a new RTL project. I have named it as an edge detection, and during the setup, we need to integrate a ZedBoard in this. So if Vivado already knows all the board specifications and settings, so it would be easy for doing this. This was the Vivado interface we have. As you can see, project summary here and what we have done in this project. This is where we need to open our block diagram. So this is the block diagram. As you can see in this block diagram, I have uh, added a module, custom module, where you can see the wizard auto-generated a Verilog file with 3 AXI interfaces, AXI light slave for control registers, and auto-generate you left it and unchanged, AXI stream slave to receive an incoming data, and AXI stream master to send and process image processing. In this project, we will using this as our main module, where we will be writing the Sobel algorithm in Verilog. We will using the two line buffers like line buffer 0 and line buffer 1 to store and the previous two rows of the pixel. This is where the Sobel algorithm will be working in this module. Coming to this block diagram, as you can see, this is the Zynq 7 processing system. This is the ARM Cortex A9 processor and with a DDR controller, and this is our custom IP. So which is where we will having the Sobel filter, and we have the AXI DMA processor memory access. The bulk image data transfer between PS and PL will be done in here, and we have AXI interconnect, where the routing of AXI buses and signals between the master and slaves will be there here. And the processor system reset, this is the processor system reset. This is where the provides the synchronized reset signals. Then we need to, after this synchronizing this block diagram, we will be running the stream generation. After the bit stream generation, there will be a run synthesis and run implementation, then generates the bit streams. After generating the bitstream, we will be exporting the hardware, including the bitstream with the certain we need to create with a wrapper, and this wrapper will be using in the VTs 23.1 version. And I need to set up the workspace. I have set up the workspace, and I have named it in a new folder with the Zynq projects. We need to create a platform project where we will be adding the .xsa file that we will be getting from the Vivado after bitstream generation. The VTs automatically creates a BSP, which stands for Code Support Packager. This is a collection of low-level drivers for every IP in our design. However, the custom IP we designed in the Edge IP, we will be using in this BSP. And coming to this C applications, we will be first creating a application project, and I have named it as an Edge app, as you see here. And after creating the Edge app, I have wrote my C code here. Before writing the C code, I have taken an image from with my phone of my hand, and then I have converted the image into image.h with 512 into 512 pixels. I have used Python script to convert this image into a .h file with the Python converter. There will be a code for Python converter. After that, as you see, this is the full code we have written. The functions like load image and int DMA. This is where we will be using the DMA, PS and PL code design, and run edge detection. This is our RX transfers XM DMA to PL and receive the edge output, and TX transfer DMA to again PL and send image. After getting all this, we need to just click on this Edge app, right click on this Edge app, and launch into hardware. after launching into hardware, we will be getting our output in zeros and ones here. I have We need to copy the software, copy this output, and I have copied it, and this is the output we are getting in zeros and ones. It will take a minimum of 20 to 30 minutes to get this output generation. As you can see, this is the output we are getting. Again, to visualize this output, we need to again using the Python script to visualize this output. Finally, we are getting this output like this. This is the grayscale input we'll be getting from the image we have taken. And this is the hardware edge output. As you can see, the white lines which we are getting in the edges. And this is the comparison image. Totally, we are using a 512 into 512 image size, a total of 2 lakhs and above pixels. And we have detecting the edges with this edges pixel with 7,900 pixels something. And a totally 1 MB of image will be bulk image transferred into DMA, which will be using for the PS and PL code design. And we have done our project. Key observations, as you can see, these are the pixels, white lines we will be detecting. This is where the edge detection comes. And in a, in extent to this project, we can add a camera module in our Vivado. In this, we can add a camera module, and we can just automate this block to get the block diagram. And again, we need to generate bit stream, and the generated bit stream will be dating .xsf file, and again we need to go to Vitis and add this and add in Vitis platform, and again run in this, and we will be getting the output as in real time. We can use it as using the camera module. Uh, Thank you.